Welcome back to another video in our series on implementing preference heterogeneity in discrete choice models. Our prior video introduced the EM algorithm as a way to make the estimation of finite mixture models more tractable. And while the EM algorithm is great, it does have some limitations that today we'll show how to overcome using a new algorithm called the algorithm, or Maximization-Minorization algorithm. The weakness of the EM algorithm is that it requires us to redo our full sequential estimation at every single step, and there could be hundreds or thousands of these steps to get to convergence. And so what the algorithm is going to do is it's going to speed up the optimization by allowing us to circumvent some of those steps that the EM algorithm has to take. The gist of the algorithm is that it, instead of directly maximizing the likelihood function that we want to maximize, it instead maximizes a surrogate function that's bounded that will get us to the solution much more quickly. And I'll talk more about that in the slides that I'll pull up now. As I just discussed, the EM algorithm requires repeated numerical optimization at every single iteration. And the problem is arising because there's no closed form solution for the weighted logit or other estimations that we might be doing at each of those stages of the M step. So if we have lots of coefficients that are not random, that are fixed, this could be exceptionally slow because we basically have to re-estimate the same model with a slight deviation and do that hundreds or thousands of times. So what the algorithm proposes to do is to use a quadratic lower bound on our objective function, and we're going to use this lower bound to create what's called a surrogate function that does have a closed form solution. But before we get too far into the algorithm, we need to at least understand some basics of nonlinear optimization. And we can go to Newton's method for optimization, which says if I have a guess for the parameter value that optimizes my objective function, I can modify that guess by taking into account information about the first and second derivatives of my objective function. So in this case, we have that the next iteration of beta is going to be the current iteration minus the inverted Hessian evaluated at the current iteration values times the first derivative of our likelihood function evaluated at the current iteration's values. So this is a tried and true, centuries-old method for finding the top of a hill or the bottom of a valley in the most efficient way possible. And so the question is how expensive is it for us to compute H inverse and the gradient of the likelihood at every iteration? That's going to determine how quickly we get to our answer. So the paper that I'm going to gloss over is by Jonathan James. He was a classmate of mine at Duke, a fellow student of Peter Arcidiacono. And this paper is in the Journal of Applied Econometrics from 2017. And basically it's showing that mixed logit models can be efficiently estimated using this algorithm that we're about to introduce. So if we go back to Newton's method, the real problem is that the Hessian of our log likelihood function for a logit model is a function of the choice probabilities, which themselves are a function of the parameters. And so these choice probabilities are changing every iteration. So whenever we change the value of our parameters, then we have to go back and recompute that Hessian. And so that's going to slow things down. So the insight of the algorithm is that we can replace these probabilities that are weighting our Hessian with a constant. And this will give us something like an OLS variance-covariance matrix to form as our Hessian, and that will dramatically speed up this algorithm. So our bound matrix is going to be a slight modification on x prime x from an OLS regression model. There's no probabilities in it. And then we just compute this inverse of this bounding matrix, which we call B inverse. We can just invert that once before we start our algorithm, and then we can use it for every iteration in our algorithm. And so this will give us dramatic speedups. If we think graphically about what's happening with this algorithm, the curve LL, which is kind of the largest curve on the screen, this is going to be the original log likelihood that we want to maximize. And it's quite complicated and difficult to maximize directly. And so, if the author was doing this justice, this would have like a lot of squiggles and some local optima, etc. But this is just a schematic of how this works. So our LL function is very difficult to optimize. Then we can contrast the EM surrogate function with the MM surrogate function. So the EM algorithm uses a surrogate function to introduce that additive separability into the sequential likelihood maximization, but we still have to use numerical optimization to get the next step in our parameter vector. So it is slightly easier to optimize than our log likelihood function. But then the MM algorithm, it's going to use a surrogate function Q tilde that bounds the EM algorithm from below, or the EM surrogate function from below, and it has a closed form solution. So Q tilde is really useful because it has a closed form solution, so we don't have to rely on the computer deriving or recomputing the Hessian every time. And all of these functions are going to be equal to each other at the parameter values of the current iteration. And so this can help us to make sure that we're going to climb up to the top of this hill like we want. So what are the advantages of the MM algorithm? Well, speed. So in this paper that I introduced, the MM algorithm has about a 5 to 8x speed up over the EM algorithm in the experiments that were run. It also is going to be memory efficient because you don't have to store intermediate data sets as part of the algorithm. You just grab your sufficient statistics from your data and then you go. It's also parallelizable because you can do these computations in a distributed manner. You don't have to have all the data in one chunk to do the updating like you do with the EM. And then finally, it's just a lot easier to code up because you don't have to code up the analytical gradient of your likelihood function and so on and so forth. So it's competitive with what's called a quasi-Newton method, and especially if we have a large amount of panel data. So again, I'm not going to get into what's quasi-Newton versus Newton-Raphson, etc. You can look that up if you're interested. But when should we use the MM and when should we use the EM? Well, the MM is going to be useful if we have a lot of fixed coefficients in our model, and if we have panel data, and if we have a really complicated model where we can't even really derive the analytical gradient. What are the limitations of MM? Well, most of the time it's going to require more iterations to converge than EM. So even though each iteration is like more efficient, it might be slower to converge than EM, especially if we have like a really large choice set in our model. So that might still be faster than EM, but it might require more iterations. So depending on where you stand and how you're paying for computing power, that might be a condition that you want to take into account. You still have to do numerical simulation in the MM algorithm. So there's nothing analytical about it. And if you have cross-sectional data, it's really not going to be helpful to use the MM algorithm. But there have been papers published by John James and his co-author Esteban Alcejo that have used this algorithm to great success. And so it's something to keep in mind as you're thinking about how can I estimate the parameters of a mixed logit model. The other nice thing about the MM algorithm that's not on the slides is that you can use it for either a finite mixture model or a mixed logit model that has random coefficients with continuous heterogeneity, whereas the EM algorithm is really only useful for finite mixture models. So I hope you have a new appreciation for the work that goes into designing algorithms that can deliver the parameter estimates that we need to then take to our policy experiments down the line. In our final video, we're going to talk about practical suggestions for implementing the tools that we've talked about in this series of videos. And we'll go over a recent paper in the Journal of Political Economy that kind of puts everything together in a really impressive manner. So I hope you'll join me for that one.